Hello, in today's class we are going to study about counters, which are nothing but sequential logic circuits. So, counters are sequential logic circuits and that are made up of flip-flops, and they are basically used for counting clock pulses. And there are two types of counters, that are synchronous counters and asynchronous counters. When we talk about synchronous counter, it will be using flip-flops, and all the flip-flops will be receiving clock pulses from a for common clock source. And synchronous counters are faster. They produce the output stable output quickly, and the design of synchronous counter is more complicated as compared to the asynchronous counter. And in case of asynchronous counter, the flip-flops don't receive clock from common clock source. Each one of the flip-flop will be receiving clock from different sources. Asynchronous counters are very simple and therefore easy to design, and the speed of asynchronous counter, they are very slow in nature. So, they are used for applications that doesn't require high speed. Um, so, we are going to study about the design of asynchronous counters and synchronous counters in this lecture. Basically, we are going to focus on 4-bit ripple counter and then modulo n counter under asynchronous type of counter, in which we will also read how to design an up counter and down counter, and same thing is also applied to synchronous counter. So, here we are going to see how to design an asynchronous counter, and we are going to focus on a 4-bit asynchronous counter, which we also call as the ripple counter. So, a 4-bit ripple counter uses 4 flip-flops in order to produce a 4-bit output, which can be labeled as Q0, Q1, Q2 and Q3. Here Q3 refers to the MSB of the count and Q0 is the LSB of the count. The input to the asynchronous ripple counter is the clock pulse, external clock pulse from a clock source, and a 4-bit ripple counter is capable of counting to power 4 number of that is 16 clock pulses, and the flip-flop is going to be triggered during the negative going clock pulse. The negative going trigger is indicated by the arrowhead that points during the transition from 1 to 0 in the clock pulse. Here we show the timing diagram of the clock pulse and the counter outputs Q0, Q1, Q2 and Q3. As you can see from the truth table, we find that the value of Q0 changes for every clock pulse. In other words, we could say that Q0 toggles for every clock pulse, and Q1 toggles for every 2 clock pulses, and Q2 toggles for every 4 clock pulses, and Q3 toggles for every 8 clock pulses. So, these clock pulses and the outputs of the 4-bit ripple counter are shown here in the form of a timing diagram. So, the arrowhead indicates that there is a negative transition happening in the clock pulses and also in all the outputs of the flip-flops. So, in the timing diagram, what we can see is that, so whenever the external clock pulse is negative going, the value of Q0 changes from 0 to 1 or from 1 to 0, and similarly whenever Q0 is negative going, we can find that Q1 is changing from 0 to 1 or from 1 to 0, and likewise whenever Q1 is negative going, the value of Q2 is changing from 0 to 1 or from 1 to 0, and finally whenever Q2 is negative going, the value of Q3 is changing from 0 to 1. So, this is the change that is happening. So, in order to achieve this, all we require is that we need T flip flops for generation of Q0, Q1, Q2 and Q3 with T value equal to 1, and for producing Q0, we will be supplying the clock pulse from the external clock source, and for generating Q1, we take a T flip flop to which the clock is supplied from Q0, and in order to get Q2, we require a T flip flop to which the clock input is obtained from Q1, and finally for generating Q3 we require a T flip flop to which the clock is supplied from Q2. So, in the slide what we see is a T flip flop. And the truth table in which we have highlighted that when the T value of the flip flop is 1, then every negative going clock pulse is going to make the flip flop to toggle. So, with this input, let us go and design the 4-bit ripple counter. For the generation of Q0, that is to make Q0 to toggle for every clock pulse, we make the T input equal to 0, we make the T value of the flip flop equal to 1, and then we apply the external clock pulse. So, whenever clock pulse is changing from 1 to 0, the flip flop will toggle, and therefore, Q0 will be shifting between 1 and 0 for every clock pulse. And then all we require is that whenever Q0 is changing from 1 to 0, we want Q1 value to change or Q1 to toggle, and therefore, for flip flop 1, the clock input is supplied from Q0 directly, and as a result of it, whenever Q0 is changing from 1 to 0, the flip flop will toggle, and hence for every second clock pulse, Q1's value will be changing. The third flip flop, what we require is again a T flip flop with T value equal to 1, and we require a Q2 value to change whenever Q1 is changing from 1 to 0, and therefore, Q1 is supplied as a clock pulse to flip flop 2. Similarly, flip flop 3 also requires a T flip flop. Flip flop 3 is also a T flip flop to which the clock is to be negative going for every 8 clock pulses, and hence Q2 is supplied as a clock pulse to this flip flop, hence Q3 is going to toggle. So, this is how we will be able to design a 4-bit ripple counter, and normally any counter should have an initial count of 0 0 0 0, and in order to clear the flip flop initially we will be using the clear input. So that with a 0 clear input, all the flip flops are cleared, and then clear is set to 1 before the counting of the clock pulses start. So, this is how 4-bit ripple counter is going to be designed, and then it is going to work. And one of the major applications of counter is it is used as a frequency divider. So, as we can see from the timing diagram of clock pulses Q0, Q1, Q2 and Q3, what we see is that the frequency of the clock pulses, if it is equal to f, we find that the frequency of Q0 is half of the frequency of the clock pulse, and frequency of Q1 is 1/4 of the frequency of the clock pulse, and frequency of Q2 is 1/8 of the frequency of the clock pulse, and frequency of Q3 is 1/16 of the frequency of the clock pulse. So, this way we will be able to use a counter for dividing the frequency of a clock source. So, this is one of the applications of the ripple counter. The most important problem with the ripple counter is that it is slow. The reason being that here the clock has to ripple through all the flip flops in order to produce a stable output, and therefore the propagation delay of the ripple counter is very large. For example, if Tp is the frequency of the propagation, Tp is the propagation delay of one flip flop, then the total propagation delay of the counter circuit is 4 times Tp, and hence uh, the counter will be able to produce a stable output only after Tp seconds, after 4 Tp seconds, and hence such counters are only applicable for low speed applications. For high speed applications, the counter is not suitable. So, in order to eliminate this particular drawback, we have to go in for synchronous counter, in which all the flip flops will be receiving clock pulse from a common clock source, and therefore, with just one propagation delay time of a flip flop, the counter will be able to produce the output. So, in the next session, we will see how synchronous counter can be designed.